This is part 4 in a series on stardust. And in this episode, we're going to be talking about dust formation around oxygen-rich AGB stars. Just as a reminder, in our previous video, we talked about the oxygen-rich AGB stars. And as the gas flows away from the star, dust will begin to form at some distance around the star. And that dust can be formed of a variety of different things. And when we're talking about the oxygen-rich case, it's going to be dominated by silicates and oxides. Now, just as a quick introduction to this, but there is a separate video that goes into more detail. Silicates are comprised of these tetrahedra of SiO4s. So this is an isolated tetrahedron of oxygens at the apices, and there's a silicon in the middle. When we have olivine, these individual tetrahedra are charge balanced by 2 2+ cations. We can also have double tetrahedra, and these form a sequence that are known as melolites. And so typically you'll have not just magnesium, but also calcium and possibly aluminum. Then we also have pyroxenes, which is where you have a full chain of these. So they're sharing 2 of their apices and you get a full chain. And in this case, you're still going to have some charge balancing, and it's going to be mostly magnesium and iron, but maybe some calcium. And you can keep building this up until you've got a full network of tetrahedra now all stuck together and not isolated at all, and they're sharing every single one of their apices. So that's just a quick introduction to the silicates. Now, I want to talk about how much material is available. So this is basically solar abundances. This is what it is like in the solar system. So we've got a little over twice as much oxygen as carbon. This is all normalized to silicon of 1 million atoms. So for 1 million atoms of silicon, we've got over 20 million oxygen, about 10 million carbon, and so on. You can see here that magnesium, silicon, iron are all about the same abundance at about 1 million. And as you go down to aluminum or aluminium and calcium, you've got significantly less. And by the time you get down to titanium, it's a very small fraction of silicon. And so what you're going to form depends on what's available to you. It's also going to depend on the pressure. And so, for instance, alumina is a very high temperature condensate. It can exist at high temperatures. And so if the pressure is high enough, it might form as high as 1760 Kelvin. But as the gas pressure goes down, the temperature that the alumina or Al2O3 will form is going to be closer to 1300. So think about this in terms of the gas is cooling as it flows away. And once it's cool enough in this range, you should form alumina. That is going to react with SiO in the gas phase. Now, SiO does form molecules, and we'll get into that in a future episode, but SiO is in gas phase, and it can react with this, as can calcium atoms in the gas phase. And so now, in this range, we're going to get this material called gehlenite. That is a melolite. That's one of those bow tie or double tetrahedra, except that you've got some alumina in there, so that kind of messes up the structure. And then this is going to react with magnesium in the gas phase. And so that's going to give you a pyroxene. So this is one of those long chains, but where the charge balancing is coming from calcium and magnesium. And finally, this will react with alumina in the gas phase again, and you'll get what's called a northite. The chances of you actually going all the way through this are pretty low, because you're also going to be, once you make this material, you're going to accelerate it. And so you may reduce the pressure too much to do this reaction. And this is going to be accelerated again by radiation pressure. And so it may not get to this. And so the combination of abundance of alumina, for instance, it's pretty low, and the dropping pressure mean that you may not actually get to forming a northite out in space. Now, another thing that can form is forsterite. This is those single tetrahedra, and this one has 2 magnesiums charge balancing it, and it can form in this range here. Now, if it forms up at this temperature here, it's going to be crystalline, but as it gets down to this lower temperature, you actually won't get crystals, you'll get something more amorphous. But this thing is unlikely to directly nucleate. It's likely to use something like the alumina as a surface on which it will form. So you'll form this, and then that will be a surface on which you can form the magnesium silicate. This will then react with the SiO. Remember, we have the silicon monoxide in the gas phase. And so we'll get something where that's now turning these single tetrahedra into chains of tetrahedra. So this is a pyroxene where you've got a chain of silica tetrahedra and magnesium's doing the charge balancing. And then this will react with iron in the gas phase. And so you'll actually break up the chain again and end up with an olivine, but it's got a mixture of magnesium and iron. So this is the individual tetrahedra again. So this is just a hypothetical way of looking at what would happen as you have a gas that is flowing away from the star and what sort of things could form. Now remember that the magnesium, silicon, and iron are a lot more abundant than the aluminium or calcium. So that's going to have an effect on which things dominate as the dust starts to form. Now, what this is showing you is the condensation temperature as a function of pressure. So this is what we call a pressure temperature or PT diagram. So I've got pressure, and this is in bars, and it's a log scale. And this is the temperature. So I've got something that if it's cooling from, say, 1900 Kelvin, and it's just dropping down in temperature, the first thing that's going to form is this black line, which is actually calcium titanate, perovskite. That is going to form first, but that's not going to be very abundant because titanium is so low in abundance. The next thing that's going to form is Al2O3, and then you can see we've got these calcium aluminates. Remember that this one we mentioned in a previous video is hibonite and is found in pre-solar grains. This one is spinel, also found in pre-solar grains. So these things are going to form as you drop down in temperature. Now let's look at these more vertical lines. These are actually what happens at different mass loss rates. So if you assume an expansion velocity, that is the flow of the material is moving out at 10 kilometers per second, and it has a mass loss rate. And in this case up here, this is 10 to the minus 3, which is unheard of, solar masses per year. Remember, we talked about it being more like 10 to the minus 6 solar masses per year. So that's this pink one here. This is what's happening to the pressure and temperature in the gas phase as the gas flows away from the star. And so what we've got is at some distance, we're going to form the first material. Again, that's this calcium titanate or perovskite. And this is going to form at a temperature of maybe 1450 Kelvin. But we're not going to form the alumina until we get down to less than 1400 Kelvin. If we were at much higher mass loss rates, so if we go up to, say, this one here at 5 times 10 to the minus 5, now we're going to form the first thing above 1500 Kelvin. The alumina is going to form at sort of 1450, 1460 Kelvin, and so on. And so you can see that it matters what your mass loss rate is. It also matters what your expansion velocity is. And that's going to dictate the precise temperature at which things are going to form. I want to point out here that the things that we think are going to dominate are these olivine and pyroxene. So this is the forsterite and enstatite. And so they are in bold. And you can see that they're not forming until you get down below about 1200 Kelvin. So even though hypothetically it could form up at 1400, it would have to be very high pressure. And at the pressures we expect around our star, it's going to be closer to 11 or 1200. And at the typical pressure, it's actually going to be so low that it wouldn't form something that is crystalline. And we'll come back to that idea later. Just to be clear, this is calculated using this equation, which is basically saying if we have a mass loss rate m dot, so that's dm by dt, and we have an expansion velocity vx, then we can say at a given radius, this is what the density of the material is going to be. And we can then plug that in to work out what the temperature pressure space should be. And we end up with an equation that looks something like this. So we have the pressure at a distance r is related to the temperature at a distance r by the mass loss rate, the luminosity of the star, the expansion velocity, the mass of the particles, and this is the Stefan-Boltzmann and Boltzmann constants. What we actually get is a dust condensation sequence, and this is where what forms depends on the density or pressure in the gas, the temperature, what is stable, and the chemistry, what is available to make dust. So here I have my star, and at some distance, it's going to be cool enough to form oxides, but not cool enough to form other stuff yet. If it's high enough density further out, then you'll get the reactions you need to make these silicates that are calcium and aluminium rich. If it's at the edge of this, you're going to start to react with magnesium. But then if the density is high enough further out still, you're going to be able to make some magnesium silicates, and they're going to exist further out. And then they're going to react with the SiO to make different types of silicates, and also the iron to bring it back to the olivines. And so these things are going to form at different distances from the star. But it really depends on what's available to make dust and what temperature is going on. And the density is going to be affected by, as the oxides form, they're going to be pushed out. So you're not going to have a nice simple 1/r² density distribution. And so when we look at an AGB star, what we should be seeing is this manifested in the spectrum of the star. So here you can see I've got alumina should be forming at the inside, and then the calcium aluminium rich silicates, and then the magnesium and iron rich silicates. And that's this shell that we just did. If we look at the spectra of AGB stars, and I'll talk about this graph in more detail later, but this is basically the spectrum from 5 to 25 microns, and then they're just offset for clarity. And these are split up into groups to kind of show you a sequence. But this is almost certainly silicates, but they are glassy, not crystalline. And then what's happening here is typically attributed to the Al2O3. So the idea is that here you're forming oxides that can form at high temperature. And as you move to higher and higher densities, you're able to then make some silicates. But this is a mass loss rate effect. And so this is just an introduction to this idea of what AGB star spectra look like and how it might relate to the compositions.